Thank you, everybody, for your patience. And without further ado, I have Osk Solom with Celery.
Yeah. So, sorry I'm late. Yeah. My name is Osk. Okay. That always happens when I say that. And I know that's a very rare name, and even in Norway it's very rare, actually. I'm currently employed by VMware, where I work on the RabbitMQ team. And we do lots of exciting things, like helping the Cloud Foundry team define what the next web stack will be. I'm also a father. We had our first son 2 years ago. I'm Norwegian, born and raised in Trondheim, while living in Oslo the later years. And just recently, we moved to London. And I started writing Celery while working at Opera Software. The first commit was on April 24th, almost 3 years ago. So we actually have a birthday coming up. So I'm sure most of you already know what Celery is. But in any case, I'll read our mission statement. Celery aims to be a flexible and reliable best-of-breed solution to process vast amounts of messages in a distributed fashion while providing operations with the tools to maintain such a system. Flexible, that means it's very extensible. Almost every part and corner of Celery is either configurable or really easy to subclass or can be instantiated separately. And reliability. This is a very hard thing to do in Python, actually. And we spent countless iterations getting the corner cases right, though you may still find ways to break it, but that is getting rarer. Celery communicates exclusively by message passing. Everything from sending the tasks to controlling the work process remotely to monitoring and sometimes publishing and receiving results. You may notice how it doesn't say processing tasks explicitly, but rather processing messages. This is because Celery isn't necessarily a job queue in the traditional sense. Rather, it's about reacting to messages as they arrive. And alternate messaging scenarios are also supported, like publish, subscribe, and broadcast. And last but not least, there's operations. The system needs to be maintained, and Celery provides the tools and framework necessary for them to do their job. Okay. I actually worked as a sysadmin myself a long, long time ago, but the angry calls left me terribly depressed. Writing your own in-house task queue may not be so much work initially, but it's likely that it will be bumping into things down the road. That's already been solved by Celery, and there's also value in having a generic system with a community based around it. I see maybe 45 new job postings mentioning Celery in the description every week, and sometimes even that many a day. And having a framework gives us terminology and a basis for expectations around these concepts. And contributing something back to Celery means that everyone benefits to it. So I realized that the proposal for this talk was a little enthusiastic, so for such a short time. So the contents will be different. Can you hear me now? Can be different from what's in the program. I'm kind of hoping that you all have some questions later so we can answer. I'm guessing that is the case. So on to the tasks. The task granularity. The amount of computation in task is called the granularity, and we say that the task is coarsely grained if it has lots of computation, and finely grained if it has less. Every single message must be transferred over the network and may be written to disk, so the task granularity must be large enough to offset the overhead of messaging. Chunking, that's a simple technique to make finely grained tasks more coarse, and it does impact the concurrency of the task. If your task is to send 100,000 emails, for example, you can slice them up, say into chunks of 100 emails per piece, so the task is composed of 1,000 tasks instead. This reduces the overhead, and it can also yield other benefits, like having access to warm CPU caches and reusing connections. At Opera, we had this feed processing system, processing lots of feeds every hour. In the database, we had one entry for every feed, and to start refreshing those feeds, we have a task select all of them from the database and send a message for them one by one. And this performed very badly, of course, and eventually not at all. So we used chunking to divide the messages into parts of thousands, and we added a countdown to each of the parts so that the load was spread throughout the available time window. And this was our first take without chunking. And if you have something like this, operating on lots of data, that should have alarm bells ringing. Simply, for every object in a database, do something with it. And you probably can't see this. If that's the case, just download the slides later. But this is similar to what we ended up with, where we divide each payload into 1,000 chunks and separate the chunks in time using the count-and argument to apply a sync. In addition, we try to limit the time to 80% of the time window available so it doesn't overlap with the next refresh cycle. But this is only a theoretical limit, as it depends on the time the task takes to run. So it may not work in practice, actually. But with good monitoring, Nagios, Munin, or whatever your favorite is, and you should have one, you'll be able to tweak the values as soon as it poses a problem. So this is a task that processes each chunk of feeds. Instead of passing the query set to the task, we send start and stop parameters so that the task can fetch the data from the database itself. If it didn't, the parent task would have to fetch all of the data anyway, and the messages would be large, containing lots and lots of data. And it may be counterintuitive, but this is a much better solution. And it ensures that any data added since the parent task is included, though that is not so relevant for this application. And later we actually added further optimizations that was even more effective, like detecting how often the feeds were updated and refreshing frequently updated feeds more often, and rarely updated feeds were refreshed on user demand. Then chords. Chords is a synchronization primitive. It's also known as a barrier, and it consists of a header and a body. It enables you to apply a callback after the task set completes, and in this context, the task set is called the header, and the callback is the body. You may notice in the examples that we use group instead of a task set. This is because we're in the process of renaming task sets to groups, because in Insight, that's a much better name, and it's used elsewhere in computer theory. And courses support natively in the Redis and Memcache RESTful backends, where they use atomic counters to immediately apply the callback after the last task completes. There's also a fallback implementation available for other RESTful backends, but it launches a task every second, polling the result until completion. And this is not all ideal, but it works good in practice most of the time. Can you see this? No. Oh, that's sad. And this is the native Redis implementation. Every task part of the header is provided with the body. Is provided with the callback, so that any of the tasks in the header can apply it. And this is available in the task request along with the task set ID, which is also used as the ID of the chord. And whenever a header task completes, it simply increments the counter, and if the counter exceeds the total number of the tasks in the header, it applies the callback. And this is the stuff Redis is great at. And it enables you to easily implement the primitives necessary for solving tasks that are not embracing parallel. And the fallback implementation, which is charmingly naive, by simply launching a retread chain of tasks that applies the callback and terminates when the header is complete. This is also a useful pattern that you can use for other things, like adding retry and timeouts to non-black workers. And I'm using a textbook example here to demonstrate chords, which is the parallel sum algorithm. Of course, the example is rather silly because the overhead makes it terribly inefficient. As in the feeds, we divide the work into chunks, then we sum each chunk, and by using the chord, we have a callback that adds up all the sums together, giving the total. So that's sort of what chords can be used for, but this is just a theoretical example that isn't really based in reality. Also, MapReduce. As you may know, MapReduce is a technique where the work is divided into two stages, a mapping stage and a reducing stage. The mapping stage gathers data into key value pairs, which is then sent to the reducers. And this slide shows the reduced implementation, a reduced implementation in Celery. And it takes two parameters, a list of results, and a reducer subtask. The result is then converted to a dictionary, and the reducer is applied for every key and value. And this is a group or a task set, if you may, so that the task and the result can be tracked as a single entity. And we also use subtask clone, which is a new thing. With that, you can clone the subtask instance and augment the arguments so that any new positional arguments added to the clone call will be appended to the original arguments of the subtask. So it's kind of like a reverse partial, I guess. And also, keyword arguments and task options are also merged with the original. And yeah, subtasks are actually just dictionaries. So, and they can be pickled, but the best practice is to call subtask on it again once you receive it, because then you can also support JSON and yeah, whatever you want. And this is the main task that with a mapper and a reducer and some data you can perform a MapReduce operation with. And it creates a chord where the header calls the mapper every part of the data. And when all the mappers are finished, the reduce task is called. Though the reduced implementation is actually kind of lame because it doesn't support intermediate data. You should really send it. For every value, you should start the reduce operation at once instead of merging them together. There's use of both. And there's an example using it in action. This is the canonical example used when presenting MapReduce, and it's counting words in data. But this does it by making a URL. So the mapper takes the document URL and returns a list of words and an initial count for each word found in the document. Right. The reduce phase then collects all of the keys, the values, and the reducer. And the reducer is called with a word as the first argument and a list of counts in the second. And it's simply returning the word and the sum of the counts, which then becomes the final result for that word. And we have a convenience method, count words, that is used instead of calling MapReduce directly. So, yeah, blocking is bad. It's like kryptonite to asynchronous I/O. But it's also bad when using the multiprocessing pool. Since every worker process has a finite amount of every worker instance, has a finite amount of processes. Having a task blocking also means blocking that worker from being able to handle other tasks. And even worse is a cluster of workers that is all blocked, of course. Because then no waiting task will be processed anymore. So this is something you need to avoid as much as possible. And one such trick is to set a timeout and retry. But if this task is CPU bound, you can try to decompose the task into smaller parts, but the most effective solution is to be smart about how you handle routing. And with routing, you can direct tasks to different workers, and you should route long-running tasks to dedicated workers, as this makes way for shorter tasks that could be of higher importance. And one idea, and one that I also would like to have built into Celery, is the ability to reroute tasks to workers that are able to handle them by using metrics such as available CPU or memory. And you can definitely do this yourself right now, but it's going to be some work. And if anyone wants to do work on this, you should come up to me and say hi. That would be great. Or work on anything, really. Or just say hi. And then there's Time. Time is new. So it took the name from a particular flower pattern in nature, which fits well into our botanical theme. But Time is a distributed service where each node manages the Celery instances of that machine. So, and it's distributed. And a Time node is called a branch. And there's no master, so it's decentralized. And every branch knows about every other branch in the same neighborhood. And each come with an embedded web server that exposes an API. And internally, every API operation may or may not reroute a request to another branch. For example, adding a new instance will send that request, will forward that request to a random branch, and very soon it will be sent to the branch with available capacity. So this is perfect for, well, platform as a service operators, I guess, and really for everyone. It even has a local mode that can replace supervisor that doesn't actually run the distributed parts. And it's got an HTTP API where you can create and manage. You can create worker instances and queues, and everything belongs to an application which provides defaults for all of the instances. And you can configure workers at runtime, configure the scale, their concurrency, and what queues they consume from, and much more I'm sure of soon. And you just have to install it by pip, obviously. Start a branch, and you can provide the directory where all of the log files are stored and the PID files are stored. And yeah, this looks much better here. My phone is better. It's much better resolution. And every branch has an ID that is automatically generated, of course. There's a command line client called Cyme, Python client, and a Ruby client. And it's just an HTTP API, so it should be easy to add new ones. And I want an admin UI. It would be cool if you could manage and add workers in the Django admin as well. That I like. So this is the client. Some branches lists the branches in that neighborhood, or actually the AMQPV host. Then we can create an app which provides the defaults for every instance created within that app. And I'm sure it can also provide some sort of scaling or sharding eventually. And it supports arbitrary arguments to Celery D and everything like that. So it works with Django today as well. Creating an instance is simple. Just there's an URL at the bottom that does the same, and that returns the instance name of the new instance. Or you can provide your own name if you want. Yeah, and as I said, that request is actually routed to a random branch. So if you have a cluster of 100 machines, then that request will be routed to one of them. And in the future, the machine with the most capacity. And the branch logs are available in the instance directory. There's log files and bid files. And we can get information like what instances there are and get statistics from them, all via the HTTP API. And you can configure concurrency when the instance is running. And that's using autoscale by default, actually. So the minimum is the amount of processes it should have all the time, but when there's load, it can grow to maximum number of processes, and it will decrease when the load decreases as well, which I don't think is that useful actually, unless you have memory limits or you're on a shared hosting provider. And the queues are referenced by name, but you can also use all of the MQP features there, so you can specify exchange routing keys and exchange types. And this just creates the queue definition. This isn't actual queue, but this is what the workers use to get the configuration of the queue. And then we can have our instance consume from it. And the logs show it consuming from it. And this is all at runtime. That's all I have, really. Are there any questions?
So one thing I didn't understand about the SIME server, I guess, is what the exact semantics are of a SIME branch. So how do they behave?
1 second here. Hello? Yeah. What was the question?
Again, about the SIME branches. What exactly are the semantics of the branches and how do they behave?
Oh yeah, okay, so that is simply every machine in a cluster runs a SIME branch, which is then responsible for watching and supervising the worker processes, the work instances that it's responsible for.
Okay,
And
so a branch is basically a physical, a machine, basically.
yeah, well, I don't think there's any point to run more of them on one machine, but it manages the instances on
Okay.
every machine, on that machine. So if you have a cluster of machines that should be able to provision new Celery D instances, then the same branch is responsible for creating, and if it stops working or whatever, it will restart it and manage the Celery D instances on that particular machine. So it's like a supervisor D, but with but a distributed one where you can create new ones, and it's like workers as a service, I guess.
Makes sense. Okay, thanks.
So maybe I should have just put this in a feature request, but I figured I'd ask. Well, here. So for a project that I work on called Media Goblin, we do image and video hosting. And one of the issues we have is once you move from video to video hosting, you can't. The always eager option obviously fails because you want to move to transcoding. So I was wondering how open do you guys think you'd be to a combo option for like Unix named pipes, or do you think that's a terrible idea?
No, I don't think that's a terrible idea. We also want one for CRM well, that's great for things like notification as well. If you want to avoid polling, you can instead send a notification to say that there's a message here, and now you can come get it.
Okay.
But I don't think that's a bad idea at all.
Okay, cool.
Hi. First, just wanted to say thanks for Celery.
Yeah, sure.
We use it a lot, and it's worked really well for what we have to do. Couple of questions. When you're going through the SIME slides, it looks like is that replacing like Celery config? Because it looked like you were doing a lot of like the routing stuff and everything.
Maybe eventually.
Okay. Which actually brings me to my next thing. So we developed on 2.2, and then we actually upgraded to 2.4 just when we rolled out some new servers. And we get all kinds of deprecation warnings because of future, you're going to be removing a bunch of stuff from Celery config.
Yeah.
Is there a reason why those are all moving to command line args versus keeping like command line args just to like override the Celery config?
Well, I'm not sure. They override the Celery config?
Well, yeah. So, like in Celery config, like we have log level set, and we have the the log dir or the log file set, and so we get all kinds of like just warning messages now. And I mean, we're going to change all of that, but
yeah. Well, that's usually just due to some stupid decisions I made in the beginning, which I don't like now, which could be just in my head. So
Gotcha.
I'm removing log files in the configuration.
Gotcha.
Because, well, it's not that flexible anyway, after all. And it doesn't work. It's inconsistent with how everything else works. I'm just trying to make things more consistent.
Okay.
But I guess it shouldn't really have to raise a deprecation warning.
Yeah, I just didn't realize why you wouldn't keep, let the command line arg override something that's set in the config.
Yeah.
But if the configs are still there. I mean, we only found out about it because we upgraded without
Yeah, but
even realizing
if
it. So
if it didn't emit deprecations warning, then how would you find out about it?
yeah. Okay. All right. Thanks.
Sure.
Yeah, hey, thanks
Hey.
for Celery as well. I was wondering if you could talk a little bit about high availability RabbitMQ.
Oh yeah, I wanted to do that. Yeah, sure. I'm kind of researching that myself right now, but so we just recently got support for high availability in a master replication setting, and it works really. All you have to do is set up something like Keep Alive D or CoreSync and Pacemaker. Pacemaker is really hard to set up, but Keep Alive D is very simple. And I'm planning on writing a tutorial on that soon, actually for the OpenStack guys. So, but it's already working. It's just a matter of installing the proxy, which is keep alive D. And maybe we'll also have support for that in the client, but then you need to maintain a static list of brokers in each client. And if you want to add a new broker, then you have to restart all the clients and all the consumers just to add a new broker. So that's kind of weird. Did that answer your question? Yeah, well, it is. Yeah.
So if we don't have any more questions, I want to ask.